Welcome to WikiPodcast. Ever considered that the simple feeling of hot or cold is actually, well, a profound window into the universe's most fundamental activity? It's not just a sensation, it's like this invisible, frenetic dance happening all around and within us
Really,
constantly.
that's exactly right. Imagine trillions upon trillions of tiny particles, atoms, molecules just constantly vibrating, bumping into each other, swirling around. Temperature, really at its core, is literally a measure of how energetic that microscopic dance actually is.
And today, we're taking a deep dive into that very concept. Temperature and thermometers truly measuring motion. Our mission is to unpack what temperature really means on a fundamental level, how we've actually learned to measure this invisible activity, and some of the frankly surprising truths about hot and cold. Stuff that might just change how you think about, I don't know, your morning coffee or the chill of a winter's day. This is such a crucial concept within thermodynamics, the study of heat and energy, and we're going to explore how we've come to understand its true nature. So, okay, let's get into it. When we talk about temperature, are we really just talking about hotness or coldness as we feel them? It seems so basic.
Fundamentally, yes, temperature quantifies those attributes we feel. But the real insight, what's fascinating here is
Oh.
that microscopically, temperature reflects the average kinetic energy. That's the energy of motion of the vibrating and colliding atoms and molecules that make up any substance. It's all about their internal motion, their constant jiggling, really.
Yeah.
The more intense that motion, the hotter we perceive the substance to be.
Wow. So it's not just a feeling, it's actually about the fundamental movement of everything. It's kind of mind-blowing to consider that even something solid like this table is actually a constant swarm of energetic particles buzzing away.
Precisely. Every single material, whether it's solid, liquid, gas, plasma, it's made of these microscopic particles. And they're always in motion. Temperature gives us a direct measure of the intensity, the average intensity of that kinetic activity.
Okay, so if temperature is about this invisible motion, how on earth did we ever start to measure? We can't exactly, pull out a tiny stopwatch for a molecule.
Right. Good question. Historically, our first thermometers cleverly relied on consistent observable changes in materials, changes that are linked to this underlying motion. Think about the Celsius scale, which most of the world uses. It's pretty straightforward. 0 degrees Celsius is set as the freezing point of water, and 100 degrees Celsius is its boiling point at standard sea level pressure.
Okay, makes sense.
And the Fahrenheit scale, which you still see mainly in the United States, does the same thing but with different numbers. Water freezes at 32 degrees Fahrenheit and boils at 212. These are what we call empirical scales. They're based on observable physical properties, like how mercury or alcohol predictably expands in a glass tube when it gets hotter, when it absorbs more kinetic energy.
So we basically anchored our early measurements to things we could easily see and reproduce, like water changing state. That makes a lot of practical sense for, everyday life. But then you hear scientists talking about the Kelvin scale. That one doesn't seem to have anything to do with water boiling or freezing, does it? What makes it so different? Why is it called an absolute scale?
Ah, Kelvin. Yes, it's truly an absolute temperature scale because it doesn't rely on those arbitrary reference points tied to a specific substance like water. Its 0 point, which we call absolute zero, represents the theoretical lowest possible point on the thermodynamic temperature scale. And what's really significant now is how the unit itself, the Kelvin, is defined. It's defined directly through particle kinetic theory and statistical mechanics.
How so?
It's defined via something called the Boltzmann constant. This constant provides a direct link between the macroscopic temperature we measure and the average microscopic kinetic energy of the particles. So Kelvin becomes a fundamental measure of energy itself, not just a relative measure of hotness based on, say, water.
Absolute zero. That sounds incredibly fundamental. What does that actually mean, though, for those tiny microscopic dancers we were talking about? What happens at absolute zero?
Well, at absolute zero, that's 0 Kelvin, or minus 273.15 degrees Celsius, theoretically. No further energy can be extracted from matter as heat. In the classical picture, the particles would be at complete rest. All their thermal motion would just stop. Now, quantum mechanics adds a little wrinkle.
Oh.
Yeah, even at absolute zero, particles still possess a tiny, irreducible amount of energy called zero-point energy. It's due to quantum uncertainty. But in terms of thermal energy, the kind you can transfer as heat, that's gone. It really is the ultimate stillness in that sense.
The idea of particles being almost completely still, that's fascinating. Bit eerie, actually. Can we actually get there? Can we reach absolute zero in a lab?
That's a really key question, and it bumps up against a fundamental law of physics. Experimentally, we can get incredibly close. We've achieved temperatures down to, I think, 38 picokelvin. That's 38 trillionths of a Kelvin. Just unbelievably cold.
38 trillionths.
Yeah, it's mind-boggling. But the third law of thermodynamics states that absolute zero can never actually be reached. It's like a horizon, a theoretical limit we can approach ever closer, infinitely closer, but we can never quite touch it.
So the coldest anything can ever get still has this tiny, tiny whisper of motion left. Huh. Wild. And this idea of stillness, it brings us right back to motion. How does something like the kinetic theory of gases, which sounds pretty abstract, how does that really help us understand and, crucially, measure this particle activity?
Right. The kinetic theory provides that direct mathematical link. It defines the Kelvin temperature as being proportional to the average kinetic energy of, ideally, non-interacting microscopic particles. And that proportionality constant, as we mentioned, is the Boltzmann constant. It's the bridge. So for a particle moving freely, like an ideal gas, its average translational kinetic energy, that's energy from moving side to side, up and down, is precisely 32 times the Boltzmann constant times the absolute temperature in Kelvin.
Okay, so it's a direct formula. More speed, higher temperature. Got it. So given that connection, how do we actually measure this collective particle motion in practice to get a temperature reading? What kinds of tools or methods do we use besides, the old mercury thermometer?
Oh, there are several really ingenious ways. For instance, the speed of sound in a gas. It turns out that's directly proportional to the square root of its absolute temperature. So if you can measure the speed of sound very precisely, you can calculate the gas's temperature quite accurately.
Huh. Using sound? Clever. What else?
Another way is by looking at electromagnetic radiation. Anything with a temperature emits radiation. For something called a black body, the frequency, or color, at which it radiates most intensely is directly proportional to its temperature. That's Wien's displacement law. It's how we can figure out the temperature of distant stars just by analyzing the light they emit.
Analyzing starlight to measure motion billions of miles away?
Amazing. It is. And even closer to home, there's electrical noise. A simple electrical resistor produces tiny random voltage fluctuations. We call it Johnson noise. The amount of power in that noise is directly proportional to the resistor's absolute temperature. So you can build a thermometer based on noise. These methods aren't about seeing individual particles, of course, but about measuring the large-scale effects of their collective energetic dance.
It's incredible using sound, light, even electrical static to figure out how fast tiny particles are jiggling. Okay, stepping back a bit. How does thermodynamics, the bigger field dealing with energy and heat, view temperature? Is it just this average kinetic energy, or is there sort of a broader thermodynamic definition?
That's a great point. In thermodynamics, temperature is formally classified as an intensive variable. What that means is it's a property that doesn't depend on the amount of material you have.
Okay, like...
Well, think about a tiny burning match versus a huge bonfire. They might reach similar peak temperatures, right? Even though the bonfire has vastly more total energy, the temperature itself is an intrinsic property, independent of the size or amount. It describes the state of the material locally. And this leads to the zeroth law of thermodynamics. It basically says that if two systems are each in thermal equilibrium with a third system like a thermometer, then they are in thermal equilibrium with each other. They have the same temperature.
Ah, right. That's why a thermometer works. If it reads the same for two different things, they must be at the same temperature.
Exactly. That law provides the whole foundation for using thermometers to compare temperatures reliably.
That distinction between intensive and extensive properties helps. So, thinking about the real world, does temperature always have to be the same everywhere within an object or a system for us to talk about its temperature?
Not necessarily, no. As long as things aren't changing too wildly too quickly, we can talk about local thermodynamic equilibrium. Think about, say, heating one end of a metal rod. The temperature can clearly vary along the rod. There's a gradient. We can still meaningfully talk about the temperature at this point on the rod versus that point, even though the whole rod isn't at one single uniform temperature. Temperature, being intensive, can be defined locally.
Okay, that makes sense for things like cooking or heating systems where temperatures are obviously uneven. It really is amazing how temperature affects almost everything. The state of matter, solid, liquid, gas, plasma density, reaction rates, even the speed of sound, as you mentioned. What are some of the most extreme temperatures we know of? out in the universe or even that we can create?
Oh, the range is just vast, almost unimaginable. At the cold end, you have things like the cosmic microwave background radiation. That's the leftover heat from the Big Bang. And it's only about 2.7 Kelvin.
Just barely above absolute zero.
Barely. And in labs, scientists create things called Bose-Einstein condensates that get down to nanokelvin or even picokelvin temperatures, like that 450 picokelvin mark.
You know.
Just fractions of a billionth of a degree above absolute zero.
Incredible control. And on the hot side.
Well, the sun's surface is around 5,800 Kelvin. A lightning bolt, that channel can hit maybe 28,000 Kelvin, incredibly hot. Then you get into things like thermonuclear explosions, peaking briefly at maybe 350 million Kelvin.
Wow.
And then particle accelerators, like at CERN. When they collide heavy ions, they can momentarily create conditions reaching temperatures of around 10 trillion Kelvin.
10 trillion? That's just, numbers lose meaning almost.
It's an immense spectrum, yeah. From near total stillness to just unbelievable levels of particle energy and violence.
An astonishing range. But okay, here's something from our reading that really made me pause. Can temperature measurements actually be discontinuous? My intuition just screams that temperature should always change smoothly, like a nice gradient. A sudden jump seems wrong.
Right. It does seem counterintuitive based on our everyday experience and classical physics. We tend to think of things like temperature as being continuous fields. But at very small scales, especially right at the interface between two different materials, say, where a liquid meets its vapor or metal touches a non-metal temperature, can actually show sharp jumps or discontinuities. For example, experiments have measured temperature differences of several degrees Kelvin right across the evaporating surface of a water droplet, a distinct jump.
A jump of several degrees just at the surface? That's wild. So these aren't just measurement errors or weird anomalies.
No, not at all. It turns out these discontinuities are actually the norm for heat transfer across interfaces at these small scales. Our understanding of this has significantly improved how we model and predict heat transfer, especially in microelectronics or nanomaterials. It happens because the ability of the materials to conduct or hold heat changes abruptly at that boundary. Heat doesn't flow instantaneously across it, allowing a temporary temperature difference, a discontinuity, to exist right there.
Huh. That really changes how you picture something as simple as water boiling or even sweat evaporating. There are tiny temperature cliffs right at the surface.
Okay, and then there's this other concept that sounds paradoxical. Negative temperature. Is there even real? I mean, beyond just being below 0 Celsius or Fahrenheit?
Yes, it is real, but in a very specific and deeply counterintuitive physics sense. You're right. On everyday scales like Celsius or Fahrenheit, negative numbers are common. Dry ice is about minus 78 Celsius. Easy. But on the absolute Kelvin scale, temperature, representing kinetic energy, should always be positive, right? 0 is the minimum.
Right.
However, physicists can define a negative thermodynamic temperature for certain specific isolated systems or subsystems, typically things involving particle spins in a magnetic field when they are knocked way out of equilibrium. In these special cases, you can have a situation where adding more energy actually decreases the system's entropy, which is related to disorder. And what's truly bizarre, completely backwards to our intuition, is that these negative Kelvin temperatures are actually hotter than any positive temperature. Wait, hotter? How can negative be hotter than positive infinity, essentially?
Because heat always flows from higher temperature to lower temperature, and heat will spontaneously flow from a system at negative Kelvin temperature to any system at a positive Kelvin temperature, no matter how high. It represents an extreme state where the higher energy levels of the system are more populated than the lower energy levels, sort of an inverted population. It's a very specific non-equilibrium phenomenon, but yes, mathematically and physically it's real.
Okay, my brain hurts a little, but that's fascinating. Negative temperature being the hottest thing around. Wow. So from that frantic jig of atoms at trillions of Kelvin down to the near-perfect stillness approaching absolute 0 and these weird discontinuities and even negative temperatures, temperature is so much more than just a number on a thermometer. It really is a window into this incredibly dynamic microscopic world that defines, well, everything.
It really is.
Yeah.
And it makes you appreciate how science evolves, from just feeling hot and cold to developing empirical scales, then understanding the kinetic basis, and finally uncovering these really deep, sometimes strange thermodynamic principles. It shows the complexity and the beauty, I think, in how physics describes the world, even for something we experience every single moment.
Absolutely. So the next time you feel something hot or cold, maybe you'll think about that invisible dance of particles, or those tiny temperature cliffs at surfaces, or even the profound limit of absolute 0. Thanks for listening. Write us your opinion in the comments on how you experience temperature in your daily life, now considering it's all about particle motion. Subscribe to the channel to help more listeners reach our deep dives. Thank you and have an amazing day.